All right, guys. So last lecture, we talked about the basic principle of counting. I hope you understood what happened there. Now we had a universe, and for each universe, we have to have one code. One code describes the universe. Each universe corresponds to one code. There is a one-to-one correspondence, and then you can create what I call Kafka protocol. Yes, and so in some situations, you have to deal with overcounting. In other words, where you have several codes representing exactly the same very thing. So here is that situation. We have two white and one black pawn. And we cannot distinguish between the white pawns because they look alike. But of course, we can imagine that metaphysically speaking, the white pawns are different. They are objects occupying different places in space at the same time. So they are not the same. Yes? So, yes, so we can obviously see, we can assign, if we want to assign the sequence of pawns, if we want to put them in order, we can represent them as 1, 2, 3, and that's a particular order, right? That's in this case, I can note whether in first position there is a white or a black pawn, whether in second position it's a white or a black pawn, etc. Clearly, the linear pattern is completely determined by the placement of the black pawn, right? So I can do that directly in this case, since there is one object that's distinguishable. So there are how many possibilities, guys? There are obviously 3 possibilities, because the black pawn can be in third position, in first position, or in the second position. Yes, and the direct codes that we can calculate here are WWB, or BWW, or WBW, right? I can keep trace of where the black pawn is going. However, there is going to be another procedure that's, for this example, it's not necessary, but it will be necessary in general, is to try to do it with the Kafka method, okay? So what I can imagine doing is I assign identities to each pawn. So there is pawn 1, pawn 2, and pawn 3, where pawn 1 and 2 are not distinguishable, yes? And if I write ordering of those elements, so how many documents do I have? You can see that the document corresponding to white, white, black, we can either have the position 1, 2, 3, or 2, 1, 3, right? I can swap the first 2 pawns at my discretion. I can swap the 2 pawns at my discretion, this and that one, yes? So there are exactly 2 documents, 2 different codes, the codes 1, 2, 3, and 2, 1, 3, that represent the same outcome, right? I don't distinguish between them. So those 2 documents are synonymous words to the same exact outcome. Now, for the outcome white, black, white, I also have exactly 2 synonyms. All right, I can basically, if black is in the middle, that means that all that I have to keep track of is that the number 3 is in the middle. And I can write 1, 3, 2 or 2, 3, 1. And for the remaining pattern, there is exactly there are exactly 2 synonyms. Each particular outcome has exactly 2 codes representing it. You see that? So here it's where 3 is in first place, here it's when 3 is in the middle place, and here it's where 3 is in the last place. Good? So this is going to be now a situation in which there are always 2 documents per one universe. Right? Always synonyms to describe the same thing. As I said in last class, maybe I said it in last class, rubbish and trash are 2 synonyms representing perhaps the same thing. Good? So how do we deal with overcounting in the event where you have exactly documents that represent well, here's how we can imagine actually doing it. Let me, before I just talk about K's and J's, let me talk about how you can imagine stocking those documents. If you're a bureaucrat, you can imagine that you will stock all files. So basically you have a piece of paper, and on a piece of paper you have a code. So in the previous example, that's the way the piece of paper looked like, right? We altogether had 6 pieces of paper because there are 6 different ways of arranging in order the entities 1, 2, and 3. Yes, the 2 white pawns and the black pawn, if I distinguish between them. So there are altogether 3 factorial documents. Now I can sift through those documents and I can create 3 piles, right? And the number of documents in each pile in this case is 2. So in this case, the pile rather than individual document represents the universe. You understand? So for instance, the pile containing those 2 pieces of paper represents the event that I'm observing, initially 2 white pawns followed by a black pawn. Good. Those 2 documents represent the situation where I see white pawn, black pawn, and white pawn. Is it clear, guys? So what I imagine is just a desk, and on my desk I have neatly arranged piles. Each pile is of exactly the same height, so it has this. Each pile contains the same number of documents. Yes, and now each pile, rather than each individual document, represents a unique outcome, right? So this document and that document are representing the same outcome. But if I put them in a pile, if I staple them, in topology you call it gluing or identification, or quotient topology if you studied such things, right? It's a similar idea here. So what you observe is this: the number of piles multiplied by the number per pile equals to the total number of documents. Do you agree? And what is the number per pile? The number per pile is the number of synonyms. So in this case, the language are the codes, and each outcome has the same number of codes as each other outcome, right? So for in English, it will not work as well because some words have many synonyms, others have barely any synonyms, right? But if you in English considered all the nouns and each noun had, let's say, exactly 5 synonyms, right? Imagine you take the English language and you isolate all the words describing all the nouns, right? All the nouns. And you observe that that each object that is described by the English language contains 5 nouns. What do? You take all the nouns and divide by 5 to count how many distinguishable objects the English language describes. Okay, to make it simple, let's avoid verbs. Let's say we call nouns. Let's say whatever is a noun, right? I don't know, a house, a monkey, a tree, right? And imagine that each of those objects had 5 synonyms. Then if you know how many nouns are in the English language, then just divide it by 5, right? And that will be how many objects the English language describes. And so of course English language does not work this way because different objects have different number of nouns. So right, so how many words can you find for a tree? And for trash, you can find trash, rubbish, refuse, or who knows, if you consider those to be synonymous. In this case, you can see that each outcome has exactly 2 words representing it, 2 codes representing it. Good? Amazing. So the way you calculate is simply the number of distinguishable outcomes is just the number of piles, which equals to the number of documents divided by the number of documents per pile. Let's try to see if you understand the situation with this example, guys, okay? I will try to be a little bit too, well, I will over-explain this example. I'm sure you will solve it much faster, but I will over-explain this particular example. Imagine that you have the pawns drawn over here. You have pawns that are of the same color, cannot be distinguishable, right? They are not distinguishable. So I can distinguish the position of the white pawns, the black pawn, and the red pawns. So how many distinguishable linear orderings are there for this situation? That's the question. You understand it, guys? So if I mean, obviously white, white, black, red, red, red is distinguishable, as is white, black, red, 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 white, right? I can distinguish the sequence in which the whites appear, the sequence in which the blacks appear, but I cannot distinguish, let's say, if I swap two whites together or I swap any two reds together, I can distinguish the difference. So how many ways are there to, how many linear orderings are there? Well, Erin, be careful. You see, maybe you're talking about how many synonyms there are, right? So I'm asking how many distinguishable linear orderings, right? The synonyms are correct, Erin. Yes, Sarah Weinflash, yes, that's what will happen. Now we will do it first. First, let's do it very rigorously, right? So that we understand what happens in other situations. So here, what do we have here? Here we have the Kafka form for the situation where I can distinguish every single pawn. Since they are not in the same space, I can imagine that each of them is issued a population number. So that's the number, maybe 1, 2, 3, 4, 5, and 6. That's the population number. Yes. So 4, 5, and 6 are the red pawns. 3 is the black pawn. 1 and 2 are the white pawns. So then I can produce documents. I will produce 6 factorial documents. Do you agree? Because arranging them in order is just all the possible sequences of 1, 2, 3, 4, 5, 6, right? So the pattern you're seeing over here is represented as 1, 2, 3, 4, 5, 6. Yes? But and that corresponds, this code identifies the distinguishable pattern white, white, black, red, red, red. Yeah? Yes. So the question now is for any given distinguishable pattern, how many synonyms will it have? If for any distinguishable pattern you have the same number of synonyms, then you can carry out that procedure for overcounting that we just described, right? So you can clearly observe that, for instance, for the outcome white, white, black, red, 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 I can carry out any rearrangement of the whites, any rearrangement of the blacks among themselves, and any rearrangements of the red among themselves. So there are 2 factorial rearrangements of blacks, 1 factorial rearrangement of the blacks, and 3 factorial rearrangements of all the of all the reds. Good. So you see that there are 2 factorial times 1 factorial times 3 factorial synonyms for this pattern, for white, white, black, red, red, red. Good. Now, perhaps, I mean, I'm not sure if you will appreciate that extra explanation, but I will carry it nonetheless. So I'm sure you understood how we counted it. Here is how I actually imagine. I imagine a separate protocol, right? A separate protocol to verify that that there are the same number of synonyms for every situation. So for example, imagine printing out documents containing every particular distinguishable pattern where you see white, white, black, red, red, and any rearrangement of those. Let's say maybe black, white, red, red, you know, something like that, right? So any such document. So then I can note the order in which the whites appear among themselves, the order in which the blacks appear among themselves, and the order in which the reds appear among themselves. You understand? So so what I imagine is that they are issued not only population number, but they're issued a sort of nationality number, right? So the white pawns are issued the identifying number 1 and 2. The black pawn is issued the number 1. And the reds are issued 1, 2, 3. They have their, you know, they have their, there is a white number, there is a black number, there is a red number, okay? And I just note how those appeared among themselves. I will put it here, just among themselves. So for instance, if you see something like this, right, you might see the code 211312, right? What does it mean? It's obviously a pattern white white, black red red red, right? So you can see that filling out this this form tells you that you have 2 factorial times 1 factorial times 3 factorial rearrangements for that pattern. And it's obvious because this form will be the same. You just have a different subscript here, a different subscript if you have a different rearrangement. You follow what I'm saying, guys? So it will be the same document, but if I look at the population, I would see maybe the colors are arranged differently, but here this form only tracks how the colors are arranged among themselves. Okay. So, for example, imagine that if the document label were white, red, red, white, black, red, and you get this code, that can clearly tell you what was the linear ordering for the population. It means the linear ordering of the population was 2, 6, 4, 1, 3, 5. Understand? If I know the downward label and I know this population code, I can translate to the document that corresponds to the population label. Again, what I strive to do here is simply identify, which I strive to identify how many synonyms are available for each distinguishable pattern. Good. So I hope I'm able to explain what I'm talking about, guys. You understand what I'm saying. It's not overly complicated, yeah? And you understand why I do this type of thing? Because I try to think like a full German bureaucrat, right? That's how you try to do, because then you know that you're absolutely efficient and that you cannot make a mistake. I'm just trying to convince you that, I mean, maybe you were convinced already by that type of drawing, but I try to convince you that each unique outcome has exactly 2 factorial, 1 factorial times 3 factorial distinguishable arrangements. That's what I'm trying to convince you of. Yes? And you're convinced, yes? And of course, I'm asking because you understand that 90% of my brain is right now engaged in rage because I cannot understand what happened to my pad and what doesn't it work. And I just started thinking about troubleshooting, right? If this thing broke or my cats broke it, what's the reason? So I'm basically maybe 10% thinking about the explanation. So you see what happens then. Then the number of distinguishable arrangements is simply the number of documents divided by the number per pile. You understand what I imagine? I imagine having stacked 6 factorial documents into piles of identical height. Yes? The piles are all of identical height, and the height of the pile is 12. It's 2 factorial times 1 factorial times 3 factorial. So each pile is 12. So then how many distinguishable? That means we have 12 synonyms for every actual distinguishable outcomes. And this is the number of words. So I take the number of words and divide by the number of synonyms. Good? Now, if you understood, try to tell me how many rearrangements of the word necessary are there, right? So, you know, how many ways to rearrange the letters to obtain, you know, other words, so to speak. Okay, very good, I suppose. All right, so let's carry it together. So again, there are 9 letters altogether. So I would say 1, 2, 3. I just look at all the letters. right? There are exactly one copy of N. There is exactly two copies of E, one copy of C, and onwards, right? So then I see that that there are 9 factorial. There are 9. If I consider each letter as distinct, there are 9 factorial arrangements of those letters. But changing the places of E's among themselves does not affect the overall, does not affect the outcome. Changing the S's among themselves does not affect the outcome. So it will be 9 factorial divided by 1 factorial, 2 factorial, 1 factorial, which of course 1 factorial is you can omit, and your final solution is 9 factorial over 2 factorial, 2 factorial. Good? Not confused, yes, guys? You're not, you're all good. I hope so. You tell me, guys, if something is, because I cannot right now appreciate my explanation, as you understand. I'm thinking about something entirely different in this class. Okay. Yeah, so here is another simple question. We have 10 competitors. 4 are Russian, 3 are from the United States, 2 British, 1 from Brazil. How many outcomes are possible if the result of this competition is only reporting nationalities ranked, but not the individual? You understand? So each Russian is just represented by, let's say, the letter R. Okay? Each US is just represented by the letter U or US, whatever you like it, right? So basically, maybe if, let's say, a person from the United States took first place, it would be US, and maybe Russia in the second place, and then two USs, right? So it's US, R, US, US. So how many possibilities are available? Think about it for a second. I'll be right back. All right, so I am assuming you got it very fast. Wonderful. Let's see what's the result. So here are the representations. B is Brazil, BR is Britain, and you have altogether 10 participants. If I consider them to be unique, I have 10 factorial orderings, but some of those orderings are masked. I do not know what they are, right? So I see that for the how many you have? You had 4 Russians, right? So 4 factorial is Russians rearranged among themselves. 3 factorial Americans rearranged among themselves. 2 factorial British rearranged among themselves, and onwards. Good? So the general situation is this. If you have altogether n objects, and one of those objects are distinguishable or indistinguishable, and 2 are in another category, among themselves indistinguishable, and so on, where n1 through nk equals to n, then the number of total linear orderings that I can tell apart is n factorial over n1 factorial, n2 factorial, nk factorial. Clear? No problem there, right? So moving on. So now we talk about combinations. So in this case, we try to understand how many ways are there to select subsets of size R from a total set of size n, where n is bigger than or equal to R, okay? And again, we will develop a way to do that efficiently, to be very bureaucratic about it, okay? So you can develop many other ways of doing that, but the point is you have to develop a very, very clear way of doing it so that you can report it in your dossier, in your document. Okay, so here is how I will carry out selection of R individuals. Okay, so I will first of all assign numbers 1 through n to each individual. So imagine each individual is holding a number, and the number is 1, 2, 3, 4, 5, the students, let's say, right? And then I place those students against the wall, and they are each standing on either the red tray or the blue tray. That's the selection and not selection tray. And there are markings on the tray, marking 1, 2, 3, etc. There are markings on the tray. Can you imagine that, guys? So they are standing in the either the red or blue tray. So the blue tray is not selected, the red tray is selected. So clearly against the wall, I can arrange these individuals in n factorial ways. And if I rearrange any of the reds among themselves or any of the blue among themselves, nothing changes. The same people are selected, the same people are not selected, yes? So what's happening here, it's like you position the individuals, and once they are on the tray, they are assigned either a red or a blue color, right? They're made to wear a red or blue shirt or some sort of thing to make them no longer distinguishable once they are placed on the tray, yes? So there are n factorial ways of placing them on the tray. And for each particular placement of individuals, if I know individual 1 through R is on the tray, and individuals n plus 1 to n are on the blue tray, I now can see that rearranging those individuals does not affect anything. How many rearrangements are possible? R factorial times n minus R factorial. Yes? So you all see that, guys, right? I'm not under-explaining, correct? It's very important. It gets very hard very quickly, and I want you to see every procedure, every step. We are gonna utilize algorithms based on algorithms we already established to work. Okay, so you need to understand that I will have a way to describe in my document that I'm using a combination, so that I don't have to go to the starting position, right? I'll develop a way to write the code for combinations. So you can see that that means that we have the number of words are the n factorial codes divided by synonyms. That's how many synonyms each of them has, right? So for example, the particular pattern of those individuals on the red tray and the other individuals on the blue tray corresponds to R factorial times n minus 1 factorial synonyms, right? Because I can rearrange numbers 1, 2, 3 all the way to R, all rearrangements that are factorial there available. And this is n minus R factorial rearrangements. So I have this formula. So we will define n choose 0 to be equal to 1. And if we want this formula to still continue to work, n choose 0 is n factorial divided by 0 factorial times n minus 0 factorial. Now, then what you are left with is 1 divided by 0 factorial. And for this to be equal to 1, we would like 0 factorial to be defined to be equal to 1. So we define 0 factorial to be 1 for that purpose, so to not have an exception to this formula. Good? Oh, hello, James.
Hi, Professor.
All right. Now we have the situation. We have 3 students are selected from a group of 4 students to go on a field trip to Greenwood. Do you know what's Greenwood? Yes? No, it's too bad. You should come with me. It used to be the place I would hold office hours at. Exactly, Alan. It's my favorite place. So 3 students will be selected to go to Greenwood Cemetery. Now, out of 4 individuals, how many choices are possible. So we can do that in two ways. So go ahead, calculate, and see if you can calculate in this case very easily, and then we'll do the more general calculation. Yes. Yes, Sarah, good, right? So first of all, in this case, it's very obvious that you can count how many possible selections by focusing on the person that is left behind, that is not going to come among the four, right? So if I have three individuals and the fourth is not selected, right? I mean, either I don't select the fourth person, or I don't select the third person, or the second, or the first. So there are exactly four possibilities. In this case, that's the easiest way to reason. Just specify a document that speaks about the person that's not being selected, right? So we can have a Kafka document indicating just the one person that was left behind. Just one number is enough to indicate, okay? But we can have another Kafka document, you see? And this is gonna be the other Kafka document we will be using. So you will have a document indicating the individuals that were chosen and the individual separately that was not picked, okay? And the way you fill that document is always you write the individuals that were chosen, you write smallest to largest number, see? Because you understand if you choose individuals, you might as well package them in the right order from smallest to largest. You understand? You can of course do from largest to smallest, but that's kind of the way I decided to indicate combinations. So I will have this box without separating cells to indicate that's one code. Okay, so it's 1, 3, 4, and 2. I cannot write 1, 4, 3 because 4 is bigger than 3. Okay, so that's not good. And then you can see that there are exactly four documents. You can see that by focusing on that box. That means person number 1 is not selected, 2 is not selected, 3 is not selected, 4 is not selected. There are exactly four documents, yes? And of course, 4 choose 3 is 4 factorial over 3 factorial times 1 factorial, which is also equal to 4, obviously, right? You see, that means I'm using a different scheme. When I do that, when I do 4 choose 3 and I say 4 factorial over 3 factorial times 1 factorial, what I do is I print 4 factorial documents of all the individuals arranged in order. And then I group them in piles. And I realize that the number per pile is 3 factorial times 1 factorial. You see that? So I have 4 factorial. In other words, I have 24 documents with all linear orders of 1, 2, 3, 4. And then I package those into piles of 6. So there is one pile that contains 6 documents, right? And another pile that contains 6 documents, and another pile that contains 6 documents, because that's the synonyms here, right? Because I would indicate like a bar here, and that's the bar of selected, that's the element not selected in that code. Okay, let's see this one. From a group of 5 women and 7 men, how many different committees consisting of 2 women and 3 men can be formed? Okay, so the second part we will do in a moment. How many committees of 2 women and 3 men? So the committee has to contain 2 women and 3 men. Okay, Andre, that's exactly right. Everybody understands this question, guys? You can calculate it. I'll wait 1 more minute and then we continue. All right. So here is the protocol that we will be using. We can say women listed by index, men listed by index. Okay, so that would mean we can put the women 25, 147, right? So they have to be listed in order. So that's the code. So clearly, the number of codes for women, we say we have here 5 women and we choose 2. So it's 5 choose 2 multiplied by 7 choose 3. Yes? You all see why. It's because once I know how to calculate the procedure for how many codes are possible in here, I just need to do the same here and then I just multiply them. Now, how many ways are there to do so if 2 of the men will not serve together? So there are 2 people that are men that will not be together. All right. Any ideas? Well, careful, Andre. Okay, James, you say something there? You have to be careful, guys. So let's see how that's to be done. Just be careful. Very simply, look at it. I can create a document in which the 2 enemies, let's say the enemies are person 1 and person 2. They don't want to be together. Yes? So I can fill in this document with person 1 and 2. Those are the documents I will count so that I know how many documents I need to discard from my total collection. You see that? So I search for documents where this code begins with 1, 2. How many such documents are available? Well, look at it. This will be how many ways to fill in the box for men. It will be 7 minus 2 because there are altogether 7 men. Those 2 are already serving and I need 1 more to complete the group. So it's 7 minus 2, choose 1. Or as somebody said, 5. Right, this number is 5. And this box can be filled in any which way you like. So it's 5 choose 2. There are 5 women, select any 2. So there are exactly 5 choose 2 multiplied by 5 codes that correspond to impossible committees. Do you agree? And all I now need to do is the total number of documents is 5 choose 2 times 7 choose 3. From those documents, I need to remove the documents that represent impossible committees. Yes? So I just take this number and subtract. So 5 choose 2 multiplied by 7 choose 3 minus 5 choose 2 times 5. Good? Okay, thank you, Andre. There is another way to do the same thing. Well, we can calculate it by addition. We can say the situation is the documents corresponding to both enemies being absent. enemy 1 in, and therefore enemy 2 out, or enemy 2 in, and therefore enemy 1 out. Okay, so in those situations, if both enemies are absent, for the men committee, I have 7 minus 2. I cannot choose the enemies, they're not available. 7 minus 2, choose 3. 5, choose 3. Yes, and here it's still 7 minus 2 because I just put the number 1 in, but not the number 2. So number 2 is thrown away, number 1 is in. I am left with 5 possibilities, and of them I need to pick 2. Everybody understands? Because in this case, enemy 1 is in. And then I have 2 more places for 2 more people on the committee. And here it's symmetric situation where 1 was tossed away and 2 is placed in. So it begins with 2. So the code here begins with 2 and 1 is not available. So again, we have 5, choose 2. And then you can write 5, choose 3 plus 2 multiplied by 5, choose 2. And so we also have the following combinatorial identity. 7, choose 3 minus 5, choose 1 is the same as 5, choose 3 plus 2 multiplied by 5, choose 2. Good?
I got a quick question.
Go ahead, James.
So, like, I can see why that's the answer, right? But also at the same time, why couldn't, because you don't, the thing is, you don't know who are the 2 men is. So why would you subtract the 7 out of the 2? Because you really don't know who's the 2 men are.
No, I mean, in this, you're right, of course, right? I mean, if I have no idea whom to remove, I imagine there are exactly 2 people though that are not gonna be friends. They're not gonna work together in the committee. So
Okay.
I can imagine that even if I do not know the individuals, right? I mean, I can imagine that there is some sort of booklet where there is a reference. So you know that the person that is of interest, to people of interest, you can label them as 1 and 2. The 2 people of interest you can label as 1 and 2, right?
Okay.
So just refer enemy 1 and enemy 2. So those are the entities, right? So that's why I imagine that the people that don't like each other are labeled 1 and 2. Yeah, and that's how I carry out this calculation, guys. So everything I said so far was not extremely fast, or was it? Right? I just worry that I did not explain it well for you. You understand? Or you need something re-explained? Or you're so confused that you have no idea what to say?
I have a quick question about the 7 minus 2.
Yes.
So that's because we are trying to find the number of situations in which the 2 men are together, and then we're subtracting that out. Is that right?
Well, so if you mean in this situation, I mean, 7 minus 2 is just how many options I have available, how many candidates I have available. So you see, the enemies are not supposed to be together, right? So the way I can group my documents. Imagine I print documents in which, well, I cannot have the codes 1 and 2 together. It cannot be 1 and 2, right? I can have 1 if I have 1, but 2 is now no longer available, or I can have 2 and that means 1 is not available. Okay, so I can break the situation into into documents where neither 1 nor 2 appear. And if 1 or 2 do not appear, they're not options. So they're 7 minus 2. Because individual 1 and individual 2 are thrown away. 7 minus 2 is how many options I have for the men. And out of those options, I have to select 3. Yes? Or in this case, I have 1 option was already selected. Person 1 is there. I cannot select person 2, so I have remaining 7 minus 2 options. 1 is there, 7 minus 2 options, and I choose 2 because 1 position has been filled by person 1. Here, it's a symmetric situation where 1 position was filled by person 2. Okay? And so in other words, this one is person 1 in, person 2 out. And here, person 2 in, person 1 out.
Understood.
And we have this situation, yes? So that's why I subtract.
Thank you.
But I think, guys, you understand how I think. I think exactly like this. I imagine I'm having a lot of papers and I'm just filling in the documents. So I have boxes and I have to write the numbers in. Okay, so obviously it's in this case easier to just subtract, right? I mean, I would say 7 choose 3 minus 5 choose 1 is the easier way to write it, I suppose, right? But those indicate different approaches to the problem of selecting the right documents.
How would one come up with 7 choose 3 minus 5 choose 1 again?
Say it again.
Like, how would you get to the conclusion that 7 choose 3 minus 5 choose 1?
Yes. 7 minus 3 is the total ways of selecting men, right? So 7 choose 3 means we'll take 7 individuals, select 3 of them to serve. And you understand how the code worked, right? I mean, 7 choose 3, you know how the calculation works. So 7 choose 3 is all of them. But how many of those documents I need to throw away? All documents that have the codes 1, 2. Here they are, 1, 2. Right? So how many documents in which I have 1 and 2? There's only one place missing, right? So that means I have additional 5 individuals. And from them, I need to select 1 individual. That's where the 5 choose 1 comes around, right? So if I just focus on the document for the men separately, just this box for the men separately, this box can be filled in, when enemies are together, can be filled in exactly 5 ways. 1, 2, and there is another code here for maybe 3, 4, 5, 6, 7. That's it, right? There are exactly 5 ways to complete this document. And documents that begin in 1, 2 are not valid. They represent situations that cannot exist. So I remove them from the pile. I throw away the pieces of paper. I have everything printed out and I remove 5 documents corresponding to events that cannot happen. Good. Here is another question. Let's see if you can do that. So 10 women, 16 men. Committee consisting of 7 women and 9 men to be formed. 5 men are friends and will only serve together. 2 women refuse to work together. So both conditions must be satisfied. How many committees are possible? Calculate. Okay. All right. So we have those documents. We have women and men. And we're going to see how many ways are there to fill in those boxes. So with the women are labeled 1 through 10, and 1, 2 are enemies. Men are labeled 1 through 16 with 1 through 5 friends. So how many ways are there to fill in the women box? Right? The easiest way to do that is, I suppose, we need a committee of size 7 for women. So we take 10, choose 7. But 2 of them cannot be together. So that means subtract 10 minus 2, choose 7 minus 2. You see that, guys, for that women box, how I carry it out. You see why it's 10 minus 2, choose 7 minus 2? Because in here, I assume that the 2 women are already inputted. So there are 1 and 2. And then we need an additional 7 minus 2 numbers to complete the code. Right? So that's the codes in which women 1 and 2 are together. Now, for the men, it's easier to do it this way, to consider the friends in or the friends out. Okay, so I would do it this way. 16 minus 5, it's where it's without the friends. Choose 9, then I need the full 9. Or I already have the friends in, and then I need additional 9 minus 5. Do you understand? So guys, you understand for the women, this is how many ways, how many codes I can write here. And this is how many codes I can write here. Now, because you have those 2 boxes, you multiply. By basic principle of counting, it's now multiplication. Yes? So we have 10 choose 7 minus 8 choose 5 multiplied by 11 choose 4 plus 11 choose 9. Yeah? So you understood what happened here, right? You all visualize the document. You all know how to fill it in. Questions? None. Wonderful. All right, moving on. So here is a question that maybe I will not answer today. Maybe I'll let you have the opportunity to think about it. We have n antennas, of which m are defective, and n minus m are functional. Defective antennas cannot stand next to each other. Functionals cannot be distinguished among themselves. And of course, defectives cannot be distinguished among themselves. How many orderings, how many linear orders are possible for this to, for this contraption to be working? You see, so it works as long as no 2 defectives are next to each other. Okay, so think about it for the next class, and we will talk about it then. Any questions about this thing? You understand how to try to figure it out, okay? So it's all a matter of what do you focus on, what do you decide to count? Okay. Okay, we're moving fast. Hopefully not too fast. All right, so we are up to the binomial theorem. So let's consider what happens when we carry out foiling. For example, if I take A1 plus A2 and multiply it by B1 plus B2 plus B3. Notice what happens. When I multiply everything through, I have exactly one instance of each A against every instance of each B. Right? So for example, A1, B1, A2, B2, right? So here, I actually listed here every combination of A1. Notice A1 is matched with every one of the three Bs exactly once. A2 is matched with every one of the Bs exactly once. And if I look at the summation, it's a summation of two terms, where the first box can contain either A1 or A2, and the second box can contain either B1, B2, or B3. Now, before I continue, could you tell me, well, I mean, you can see it in the picture, obviously, but how many possibilities are there? How many summands are there? How many terms do I add up? You see, this is a sort of like a protocol here as well, right? What goes here, what goes here. Yes, there are exactly 6 possibilities here, right? You can see that obviously, but do you see why 6? Because it's 2 possibilities here multiplied by 3 possibilities here. So you have exactly one combination of an A against a combination of B. Now, let's see if you can help me with this example, okay? So what happens if I have a bunch of A's in one parenthesis multiplied by a bunch of B's in this parenthesis multiplied by a bunch of C's in this parenthesis? You will hopefully see that what I will have, every term that I'm adding is going to have one instance of A, one instance of B, and one instance of C. Yes? So in this case, it would be 2 possibilities for A, 3 possibilities for B, and 4 possibilities for C. And as somebody already replied, said, well, careful, Fiona, not 12, but 24, as Grant said, because you have 2 times 3 times 4. Yes? Good?
Yes. Yes.
Wonderful. Good. So you see how it goes, guys. 2 possibilities times 3 possibilities. And you, I hear from a few of you, but those I don't hear from. You understand how that's working, yes? You understand that just FOIL it out and you see basically A's together with B's if you open up the first parenthesis, if you follow the first 2 parentheses. Now, that expression you multiply by C's and you will see that each monomial, or whatever you call it, each summand will gain a C, exactly 1 C. So that's just a particular observation about multiplication that we'll need. Okay. Now comes the slightly hard thing. Now, how to expand x plus y to the power of n? How do we expand? That's the binomial theorem. So we have x plus y to the power of 1. It's just x plus y, right? Nothing happening. Nothing interesting is happening. Now, if we have square, I can imagine, I say I indicated the 1 here, but you can imagine that there are 2 parentheses. There is parenthesis 1 and there is parenthesis 2. I distinguish it as the blue and the red parentheses. Good? So, so there is, I just make this distinction. So notice what happens. So the first box represents a contribution from the red parentheses, from this parenthesis. The second box represents a contribution from the blue parentheses. If I don't simplify, how many terms do I have? How many additions do I have? If I keep the distinction that blue parentheses is different from red parentheses. It's a question, guys, not rhetorical. 4, exactly, James. Exactly, Grant, and everyone else who is saying there are exactly 4 possibilities. Hopefully, you all follow what I mean. 4 possibilities. This box is either X red or Y red, and this box is either X blue or Y blue. Yes? So then when you simplify, look what happens. When you simplify, because you can only distinguish X's and Y's, right? So you have either 2 copies of Y or 1 copy of Y or no copies of Y. You understand? I can once I write the summations, I can group together by the number of copies of Y that I have. You understand? So why am I grouping it into 3 categories? Because you either have 0 copies of X and everything is Y, or 1 copy of X or 2 copies of X. There are no other possibilities, right? So even though we have 4 terms that we have here, 2 red contributions, 2 blue contributions make together 4. We can collapse it to 3, right? We can collapse it to 3 based on how many X's we have in a pile. Yes? So this means that I received Y1, Y2. That both, I should have colored them maybe red and blue, but I hope you understand even that it's all red here, right? So from the first parenthesis, I had to have a Y, and from the second parenthesis, I had to have a Y. Same thing in the, so what happens here? What happens when I have X times Y? Y is the coefficient here too. Because there are 2 ways of obtaining X times Y. Either the first parenthesis contributed an X and then the second contributed a Y, or vice versa. First parenthesis contributed Y, second parenthesis contributed X. And to get X squared, there is only 1 way to do that. So you see the coefficient here represents how many ways of selecting 1 X and 1 Y. Now let's see if we can understand what happens when I carry out X plus Y to the power of N, for N being some large integer. Maybe it's 3, 4, 5, 6, 7. Do you all see that when I multiply it out, I have first parenthesis, second parenthesis, all the way to the nth parenthesis. I can distinguish parentheses when I expand. First parenthesis, second, all the way to the nth. Yes? And if I multiply things through, look at it. This element will be first parenthesis. This element will be second parenthesis, third parenthesis, all the way to the nth parenthesis. How many summons will I be having? How many terms do I add up if I don't simplify? You understand that when you just realize that what it boils down to is that when you multiply the expression through, you have something here, which is either X or Y. Something here, which is either X or Y. This is reserved for the contribution from first parenthesis. Grant, Sarah, you're correct. Ben, you're correct. And Grant, did you mean 2 to the power of N and you accidentally rolled the X? Because it's 2 to the power of N. You see, it's 2 multiplied by 2, multiplied by 2, multiplied by 2. It's 2 to the power of N. If it's X cubed, so if it's X plus Y cubed, then you will have 8 contributions, right? You would have 8 summons before you simplify. Clear? So there are 2 to the power of N summons, which can be grouped according to the number of X. Okay, I will group them now according to X. How many X do I have? This means I have 0X. This means I have exactly 1X. And then the next will be I have exactly 2X's, etc. So how many ways to create Y to the N? What do you think? What's the coefficient that goes here? Careful, how many ways to create Y to the N? It means each parenthesis, first parenthesis had to contribute Y. Second parenthesis had to contribute Y. All of them had to contribute Y. So there is exactly 1 way to do that, right? What about the next situation? How many ways are there to get X times Y to the power of N minus 1? You see, how many ways can that be the pattern? You see, I'm grouping patterns where there was 1 contribution of X and the rest were contributing a Y. How many such patterns are possible? Okay. Jeffrey, and what about the rest of you? And of course, I would like to know if anybody would be willing to explain their reasoning? Okay, James, that's good. Think about the reasoning and, you know, do you see it? Jennifer, n choose 0, you're saying that's for maybe the first, but for the second element, it's not n choose 0. So what happens here? Here, the x could have come from the first parenthesis, or from the second parenthesis, or from the third parenthesis, or from the nth parenthesis, and the rest would have been y's. Yes? So this would be n. This number is n, as James said correctly and a few other students said correctly. Yes, this would have been n. You all see that? Okay, and choose 1, exactly, Jennifer. Now, could anybody be willing to tell me, that's the hard part now, how many terms are going to be of the form x to the power of k, y to the power of n minus k? What's the coefficient here? And of course, y. Maybe you have seen the binomial theorem before. Y is more interesting to me. What's the coefficient here? Okay, Andre, that's great. Let's see what other people say, but I would especially appreciate knowing what are we choosing. Okay, what does the n refer to and what does the k refer to? Well, more specifically, what are we selecting, right? So when you have a form, somebody comes to you and he's gonna ask bureaucratically, and what are you selecting, right? So you have to answer, what are you selecting? What specific object are you selecting and what fate are you preparing for that object? Or if you prefer to say it in German, welches Objekt wählen Sie und was wird das Schicksal dieses Objekts? Did it help? What object are you selecting and what is the fate of that object?
Isn't that with the x bonus, right? One of the x bonus has to be 0. So x in the beginning will be like 0, right? And y at the
Yes, the sum of the exponents has to add up to n all the time, because you can see that this bar is of length n. So however, you can fill it with how many x's or y's you like. The total number of x's and the total number of y's adds up to n. That's why we have the summation equal to n, if I understood what you said, James. Okay, so anybody wants to tell me? No? So let me tell you what are you selecting. So the k that you're selecting are the parentheses. You see, you have first parenthesis, second parenthesis. You are selecting which parentheses will go and have which fate. Those are parentheses that are designated to be x. Do you understand? And the other parentheses will be designated to be y. So n choose k, meaning which of the n available parentheses will be contributing an x. K will be then the x. Make sense? That's why you have x to the k. So the coefficient here is n choose k. Because if I have x to the power of k, that means that k, exactly k out of n parentheses, gave an x. They gave birth to x, and the rest of the parentheses were assigned to y. Do you understand? You look, some of you look silently confused. But it's good that I can see that you look. So do you see how I get to the conclusion n choose k? Yes, but not only after class. I mean, we will have office hours and we will play a little game, by the way, right? That's going to be our strengthening, right? Because anybody who takes my class now will be playing that game, which is called What, When, Where, if we translate it to English. Well, right? Well, James knows it, right? So again, guys, we have n choose k. N referring to the parentheses and k referring to their destiny of becoming x. N of the parentheses, sorry, k of the n parentheses will be made x, will contribute an x, okay? Good. So to let you digest this a little bit, I will pause the lecture at this very moment. I will stop recording and we will go to office hours. If you would like to wait, one question that we'll do is we'll play that game What, When, Where, and then we will answer one or two questions we'll play as introduction, and in general we'll play maybe one question per office hours, and then we'll do office hours. Good? So let me show you what that game is about.